Okay. Thank you. Doubling our positivity. Please, JJ.
Fantastic. Wow, what a genuine pleasure to be here. I'm going to start by telling you what my goal is in giving these lectures. I noticed that my title and abstract haven't appeared on the site yet, so maybe it seems a little mysterious. What I genuinely want, is for all of you to appreciate and have the tools necessary so that if you feel like it, you can join us in some very large, very intricate calculations involving gravitation. So what I want to do is so I know a lot of, I've already spoken with a number of people who have expressed, ooh, well, wouldn't it be nice if, the things you're talking about, I could start including mass, if I could start including, different matter of various types. And what I'm going to try to do is I'm going to try to present the way we calculate in such a way that it's actually relatively easy and straightforward to understand how this has been generalized away from the literature. So I'm going to start very, very basic. We're going to start at 3-point interactions and then move upwards. But just to give a sketch of the path, so my ultimate goal is to make it easier for you to calculate in gravitational theories. And the path, the strategy is to get good at calculating in gauge theories. Like Yang-Mills and related gauge theories. And what we're going to do is we're going to exploit the double copy structure of all sorts of field theories to lift information that we discover in predictions of gauge theories to extract predictions from gravitational theories. Okay, so getting good. With gauge theories. All right, and so what we're going to do to get good, at least relative to what we might naively do, just from our quantum field theory education, just taking our actions, writing down Feynman rules, and then jumping up and down forever, is we're going to try to, whenever possible, use a minimal, unique information relevant to any prediction, relevant to any tree-level prediction, relative to any loop-level prediction. We want to minimize the amount of information we ever have to write down. And the tools we'll use for this in gauge theories is the duality between color and kinematics. And unitarity methods. So the duality between color and kinematics actually tells us that there's a tremendous amount of redundant information in scattering amplitudes, even in gauge theories, and this lets us focus on some minimal set of building blocks that we can use. And along with the duality between color and kinematics comes the associated double copy, which lifts us to gravitational theories. But beyond this, the way we're going to construct our predictions is we're going to recycle easier predictions we've already made. And so We've already heard Yara and Shruti and probably a number of other people mention unitarity cuts. We're going to use the fact that physical predictions factorize on physical channels into products of physical predictions to really minimize the amount of unique information we ever need to introduce when making calculations. So, by the end of these lectures, I want you to be able to understand how to put an amplitude in a gauge theory into a color basis. And the reason is this exposes gauge invariance. That's the first thing. The second thing is I'm going to teach you a way to find kinematic numerators that obey the same algebraic relations as color factors. And that's what's going to allow us to minimize the amount of independent data we actually ever have to write down for any given gauge amplitude. And we'll talk about replacing color with kinematics. To lift linearized gauge invariance to linearized diffeomorphism invariance. Right, and this is the double copy. And this will certainly get through by the end of this first lecture. Then, with regards to unitarity methods, the first is super easy. I'm going to teach you or remind you how to draw all relevant graphs. To amplitudes, or what I'll call full amplitudes, these are the things you actually square when you're getting a cross-section. So actual full amplitudes in a theory, full amplitudes, as well as ordered amplitudes, which are the gauge invariant building blocks that sit next to color weights once you've gone into a color basis in full amplitudes. These are smaller. These grow factorially. Factorially is horrible. These grow exponentially. That's much more happy to deal with. You combine this with isomorphism symmetry and the reduction in independent graphs under a color dual basis, then you're really cooking. Then you've got a very small amount of information you need to wrap your head around to get predictions. All right, so we're gonna learn to draw all relevant graphs. We're gonna learn how to dress them. In 3 different ways, according to some L loop integrand. And this is easy. So this is going to be sort of beginner level, right? according to sewing lower loop amplitudes on cuts. And this is definitely where the professionals make their money, right? This is how we can verify that we've written down the right integrams at the multi-loop level, and this is an awesome way to construct. But if you have aspirations to going to 7 and 8 loops in gravity theories, you're going to drown in information. And so we want something even better, so that you don't have to necessarily evaluate all the cuts by sewing lower loop amplitudes. But we're going to talk about, and this is what I hope to get at by the end of the second lecture, how you can recycle knowledge of a basis of ordered cuts, say, like the planar sector, and tile that outwards. To reconstruct full amplitudes. All right, and so that's where we're going. So what I'm gonna hopefully give you the tools to do is to, and I'll do this mostly in the example of Yang-Mills and maximally supersymmetric gauge theories, maximally supersymmetric gravity theories, but hopefully by providing enough detail that it is straightforward for you to generalize to the theories you care about. And I'll talk about where things generalize as we go. All right, are there any questions before I jump in? All right, I think it's time to get started. So, now, the first time I ever had to give lectures on something like this, I think, is when I was invited to give TASI lectures. And so I thought, oh, okay, the best place to start is obviously 3 loops in the maximally supersymmetric theory. That's going to be, everybody will follow that, no problem. It turns out that some people followed it, but what I'm going to do right now is I'm going to start with 3 points. 3 points tree level. And what we're going to do is we're going to see why we need structure constants. So we're going to get good at, I'll try to stay under the glare line, at ABCs being antisymmetric. And why we need them. Okay, and so for this, we'll look at 3-point kinematics. And like everything, I'm going to be talking about all external particles being on shell, all external particles being physical. And so at 3 points, the kinematics is incredibly simple. Conservation of momentum. Oh, so unlike Yara, who I think was using Yara was using K for loop momenta, I'll use K for external momenta, sometimes P, sometimes K. I'll use L's for loop momenta. All right, so conservation of momenta, everything's on shell if I'm dealing with, I'm going to talk about massless particles right now. The only thing having mass would do is it would introduce building blocks that are equivalent to the invariant mass squared, which is just a simple generalization from what I'm talking about right now. So we'll just stick with massless right here. But this already has tremendous constraints. This means that any Mandelstam, any momentum invariant just involving our external momenta has to vanish. Okay, so if we're going to write a gauge invariant amplitude, we're already out all sorts of interesting things at 3 points. There's almost nothing to write down because so I'll use Sij to mean Ki plus Kj squared. So any Mandelstam invariant, just scalar Mandelstam invariant, vanishes. Now, if we're going after vectors, we're going to need a polarization vector for each external leg appearing in every term. Oh, so I'm also going to work in d dimensions. So I'm not going to stay restricted to 4 dimensions. Not because 4 dimensions isn't spectacular, it is. We've already seen a number of different examples of how, while you're staying in 4 dimensions, you can get incredibly compact expressions. One reason I'm going to allow myself to generalize to d dimensions is because d-dimensional unitarity cuts let you capture all the information relevant to cuts. You don't miss what would be rational terms under 4-dimensional cut construction. So if we're working in d dimensions and we're regulating with dimensional regularization, we're not going to be missing things as we're going to loops. Okay, so what are we going to need for vectors? So our vectors require a polarization for each leg in each term. Okay, so we can end a scattering amplitude has to be we're gonna insist on Lorentz invariance, so we're doing relativistic quantum field theory, so we're gonna insist on Lorentz invariance. And so there are only so many Lorentz invariants we can start writing down. Let me just remind you of one of the chief features of a polarization vector. So what happens when I dot a leg with its polarization? What do I get? 0, right. Yeah, polarizations are transverse. Okay, good. So I don't have to write down epsilon1.k1, but I do have to write down epsilon.k2, right? And let's say epsilon1.k2. I could write down an epsilon1.k3. I can write down epsilon2.k1, epsilon2.k3. epsilon3.k1.k2. Okay. But of course, these aren't all, well, what else can I write? I can also write down epsilon1 dot epsilon2, epsilon1 dot epsilon3, epsilon2 dot epsilon3. Okay, I've written down all the momentum invariants I can think of that don't trivially vanish. But this is overcomplete because of conservation of momentum, right? So, right, epsilon1.k3 is actually equal to the negative of epsilon2.k3. Yeah? Everyone see it? Sorry. No. I went the wrong way. I meant to go with my case. Good. Thank you. So, like this. Like this. Right? So K2 is minus K1 minus K3, and the K1 dot epsilon 1 vanishes. Right? So these guys are not independent. Yeah? These guys are not independent. and these guys are not independent. Yes? Everybody follow? Yeah? Okay, good. So it turns out I only have so many building blocks to start writing down an ansatz for what an amplitude could be at 3 points or vectors. Right, so this is just a guess. All right, and then we'll impose physical properties on it beyond just, beyond the possibility of being gauge invariant and being manifestly Lorentz invariant. All right, so let's start with some epsilon1 dot epsilon2. And since every term needs each polarization, right, we'll add an epsilon3, and the only unique I was K1. And so this will come in with some coefficient at alpha 1, alpha 2, epsilon 2 dot epsilon 1 dot K2, epsilon 3 dot epsilon 1, epsilon 2 dot K1. Right? And these are the only things I can write down, right, with these building blocks such that each term has a polarization, right? Each term has each polarization. Yeah? Cool, but what do I want out of my scattering amplitudes for 3 vectors is I want Bose invariance. And so, right, what does that mean? That means in this case, right, that it should be, you know, swapping legs 1 and 2. Or any permutation of legs. Yeah? It should be a Bose invariant quantity. It should be Bose symmetric. Yeah? Right? I impose that on this, and I go back to my basis using conservation momenta, and I find this has to be 0. Right? There is nothing compatible with these building blocks as written and Bose invariance. This constrains all of my free parameters. Imposing Bose symmetry. All right. Okay, and this is consistent. This is consistent with there being no 3-point interactions in Maxwell's electrodynamics, right, in U1. Right, but if I want to be able to satisfy Bose invariance, and it's real easy to see why this is happening, is as I swap terms between, for example, K2 and K3, I just pick up a minus sign. These building blocks, they want to be antisymmetric. Right? So the only way I can satisfy Bose invariance is if I actually give extra information to each of my vectors, and that'll be the color weights. All right, and so now what I'll do is, rather than a full amplitude, I'll just grab some kinematic bit. I'll call it this, right? And so the picture here, 1A, 2B, 3C, is that as I swap any of these legs, this guy will swap, and these guys will swap. And I know that the only thing I can get is something that's anti-symmetric and swapping here. So this guy has to be anti-symmetric. Forces, so non-trivial. And this is true. At this mass dimension, that's all I've shown you right now, is I've shown you this mass dimension with 1K. Turns out we can consider one other mass dimension for vectors, and we'll do that in just a second. For this mass dimension, there's nothing you can write down that's symmetric in the legs, that's non-vanishing for all external vectors. Okay, so just write down what the building block ends up looking like. Right? So after I impose Bose symmetry on this guy, allowing this to be antisymmetric, so allowing this to be fully antisymmetric, I get something really nice. I've got some, overall constant of proportionality. We can associate that with the coupling if you like, right? And then right, so this is the building block. All right, epsilon 1 and epsilon 2. What I did is I just made the fact that these guys are equivalent manifest by subtracting one from the other. And if you like, I'm absorbing that factor of 2 into my overall constant. Yeah? Good. So we've got something that's manifestly cyclic and manifestly antisymmetric. And this was forced on us, right? Turns out, as I said, okay, so this is the 3-point amplitude you do get from, of course, our favorite trace f squared. That's not the only operator involving vector fields that has a 3-point amplitude. But it's the only operator of this mass dimension. Turns out there's one more thing I can write down. I can't climb mass dimension at 3-point trivially by multiplying by Mandelstam invariance. They're all 0, right? So I'm left with how I can combine these blocks. The only other thing I can write down is something like this. The only other mass dimension that admits having a polarization per term, right? It's trivially gauged, so these are trivially gauge invariant, because if the Ward identity, right? So what's the Ward identity I'm looking for? I'm looking at taking my amplitude and replacing any epsilon, any polarization with its momentum. My amplitude has to vanish. Because my Mandelstams vanish, that's trivially satisfied anytime I turn an epsilon into a k. I just start getting zeros, right? It's absolutely the case here. So this is gauge invariant. And turns out this is trace f cubed, right? So the simplest higher derivative operator you can write down that's consistent with vectors. It's also, by the way, manifestly antisymmetric. So it'll only show up in a full amplitude, again, if it's dressed with something that's antisymmetric. Any questions? This whole exercise was just to show you that the constraints of requiring something that's Lorentz invariant and that's something that has the possibility of being gauge invariant forces us to have some sort of antisymmetric color weight, right? We know this isn't all there is to Yang-Mills. We know that there's something coming at 4-point for gauge invariance, right? But we've discovered that our color weights and our kinematic weights have to be antisymmetric at 3 points. Now, I started with vectors because I love vectors, but I just want to say a few more things at 3 point before we go to 4. Okay? All right. Well, what about scalars? All right, so okay, well, it could be equal to a constant, right? Some number. I don't know. Right? Like trace phi cubed. This is nice and Bose-symmetric. But I can't write anything in terms of Mandelstam's, right? So little group scaling really severely limits what I can even write down for 3 scalars interacting. I'm allowed to have a symmetric, so some sort of DABC, right? Or as many copies of DABC as I want, right? I'm allowed to have FABCs if they come in pairs. Right, so again, the idea is that each leg would carry 2 color indices. That's supposed to be a capital C, little tiny lowercase c. All right, so I can have FABCs at 3 points as long as they come in pairs, right? So I can have some sort of bi-adjoint scalar for the 3 point. I could have something that's purely symmetric, like a trace phi cubed, or just a normal phi cubed. Slightly more interesting is if I let it start interacting with stuff. Right, so I could have something like 1 phi, 2 phi, and a vector. Right? And in terms of my building blocks, there's just not very much I can write down at all. I can have a right? That's basically it. Yeah? 4 for something that's antisymmetric. Oh, I should emphasize, I don't even know where I should write this. I'm going to write it over here. I'm using an all outgoing convention. Everything I'll be doing, I'll write my external momenta such that the sum of my ki is equal to 0. So I'm always using an all outgoing convention. What can I do? Another thing I can do is if I distinguish my scalars in some way, let's say I've got complex scalars, then I do admit something like this without violating Bose, right? And this is related to the fact, well, I can even take this down to U1. That I can couple, I can have a scalar electrodynamics as long as I've got complex scalars to carry the charge. I want to talk about just one more interesting case. Write down. Right. And so, wait a second, just while I'm here, what's this? So this is exactly what I get from a covariantized free scalar, right? Where my scalars are in the adjoint. What about something like this? What about 2 vectors and a scalar? Can I have 2 vectors and a scalar? It turns out you can. So Yeah, so I can have an amplitude proportional to this. And what I'd like you to notice, right? And so this is the only thing I can write down. And this shows up like a graviphoton coupling to a gravscalar. But one thing we see here is this is a lot like taking our two-scalar amplitude, two-scalar one glue. So this is our two-scalar one glue right here. Taking our two-scalar one glue and multiplying it by another two-scalar one glue. In fact, it's exactly that. And what you see is by taking this product, I end up with something that indeed has two polarizations, one for the 2 and one for the 3. So what was this? So just reading it right here. And I'll just keep one of them. So I'll just write K2 dot epsilon 3 here and K3 epsilon 2 here. All right, by taking the product, I absolutely have an expression that is gauge invariant and has the little group scaling in the product that is the product of the little group scalings of the building blocks. And this is actually probably the simplest example of a double copy construction I can write down, where you'll notice I pulled off the color weight and I replaced it with a kinematic weight that had the same behavior. Right? But that leads us to asking about gravitons. What about spin 2 fields? Okay, and for this, I think I should probably go a little bit more into detail about what I mean. Well, I should go into a little bit of a review about the properties of vector polarizations and remind you that the tensor polarizations factorize into vector polarizations. So, vector polarizations all right, so in D dimensions, I've got D minus 2 different physical states, different physical polarizations. This is my external momenta. And this is a reference momenta, a reference null momenta. It's a reference null momenta that exists to exhaust all gauge freedom, right? So again, so in 4 dimensions, we've got 2 physical states for photons, right? But this is manifestly, it's a 4 vector. So there's extra stuff we're carrying around that we need to project out. And that's the whole job of this reference null momenta. So Q dot P should not be 0. That's one of the jobs, but P dot epsilon All right, so our polarization has to be transverse with respect to its momentum and also with respect to the reference momentum. And then we've exhausted all our gauge freedom. All right, and this guy carries the little group weight, the little group scaling associated with being a spin 1 vector. All right, what do we want from gravitons? So, as I said before, tensor polarizations, we can factorize as into vector. For spin 2 gravitons, what do we want? We want some symmetric, traceless, and transverse. And since it factorizes into vector polarizations, we can actually write all the states in terms of a basis of vector states. All right, but maybe I should emphasize, so transverse, I mean that P nu epsilon mu nu and so there are 1/2 d minus 3 of these in d dimensions. So in 4 dimensions, again, we get 2. And so we can express these polarizations specifically in terms of the same exact vector polarizations we had before by appropriately symmetrizing. And subtracting out the trace. Okay, good. And here, let me give a tilde here. And the reason I'm giving a different tilde here is to just emphasize that these polarization vectors don't need to be the same. Right? They just need to be polarization vectors. I don't need to have the same reference momenta in here. I do have to have the same momenta. The p has to be the same. Right? This is a function of p, right? All right, good. Let's see if I have space over here. I do have space over here. Physicists have a few good tricks that we use again and again and again. And one of the best few tricks is inserting the identity between things, especially in quantum, right? In this case, we've got a completeness relation for physical states. What's the completeness relation for polarization vectors? Right, so I'm summing over basically back-to-back polarizations on the same momenta over all physical states. I project to, so I've got downstairs mu nu. So I project to basically just dotting whatever these guys were dotted into. I'm dotting them together. P mu q nu plus q nu p mu. Nope. Q mu p nu over p dot q. All right, and so this is a physical state projector, right? And this is what lets us sum over all the on-shell physical states d-dimensionally when we're sewing trees of gluons together with each other. And in fact, it's doing this in d dimensions that allows us to, using d-dimensional cut construction, recover the all plus amplitudes, for example, in pure Yang Mills on d-dimensional cuts. So let me just say with the completeness relationship, the completeness relation is for gravitons, what does identity look like when I'm summing between gravitons? And then I'll keep going. So again, so if I have mu nu equals the gluon projector, if you like, minus beta mu nu plus E nu plus B mu Q nu. Right? If I've got my gluon projector, then the graviton projector, the state sum mu nu. Rho sigma. Just wanted to get this on here. Already, I think you can, okay, so this is what we get. This is what we get from squaring our gluons, right? Or squaring our vector polarizations. But if we're really talking about gravitons, then we have to subtract out the dilaton as well, yeah? All right. Good. Yeah. The other terms. Oh, okay, so these are the same term, right? Under conservation of momentum. I just wrote it twice. Yeah. Minus K3 minus K2. Right. So if I dot this in with epsilon 3. Yeah? Yeah? Is that okay? Good. The only reason I did it was just to save chalk and space. Sorry if that was confusing. Okay, good. But what we're going to do now is, okay, so I said we were doing this because we wanted to write down a graviton 3-point amplitude. All right, and so what would it look like? What would it have to satisfy? So we see a calligraphic full amplitude, right? We want two polarizations, polarization vectors for external leg. Good. And so we could imagine writing down something with just 6 polarization vectors dotted in with each other. But since you don't have any Ks, since you don't have any momentum, there's no chance of gauge invariance, right? I'm just could try an ansatz. With no external momenta. Just, 6 epsilons dotted into each other, right? Something of this form, yeah? But of course, it can't be gauge invariant. The first thing I could possibly get is having 2 Ks, or if you like, two derivatives, right? It turns out all the criteria, so we want two polarizations, want to satisfy linearized diffeomorphism, and all these properties are satisfied. If I appropriately symmetrize, right, as I wrote down over there, if I appropriately symmetrize over my polarizations, such that I don't have any antisymmetric tensors, and so I don't have and I remove the trace, right? Then this absolutely satisfies all the criteria I needed. In fact, this is exactly what you get if you write down Einstein-Hilbert, you expand G in terms of some H over the background, over maybe flat space, and then work out the Feynman rules as DeWitt did. And it's 171 terms in the 3-point Feynman rule, off shell, but on shell, right? When you impose on shell conditions, it all collapses to this factorization. Okay? All right. Of course, and when I said 2Ks, then clearly, and I was writing it like this, hopefully it was obvious I meant taking the Yang-Mills 3-point amplitude and the Yang-Mills 3-point amplitude. There's nothing that stops me from double copying one of them with a cubic, the trace phi cubed, or both trace f cubed, or both of them with trace f cubes. And those correspond to different gravitational higher derivative operators. Good. So let's summarize. Let's summarize what we've learned so far. Because I know this, this is both basic, and I was going kind of fast. But I did it in this way because I wanted to give you some comfort and a playground to start playing around with writing things in terms of building blocks, say momentum invariance, and then imposing physical constraints, right? Because that's how that is absolutely how we're going to go after higher and higher loop calculations. Yeah. And what did we learn? We learned that Yang-Mills needs color factors. We learn, and so in the context of Yang-Mills, and this is something that will generalize to all multiplicity and to all loop level, every graph in Yang-Mills will end up having some color weight. And it turns out that'll come from products and sums over shared indices of these color factors, some kinematic weight, right? And this is where our polarizations and our momentum dependence will live, our derivative dependence up in the numerator. And then, of course, it'll sit over the massless propagators that the propagators you get in general for Yang-Mills, or for any massless particle. And for the most part, I mean, there'll be times in what I do in the rest of this lecture where I actually, I'll actually plug in for the propagator structure, in a particular theory, and we'll say, oh, if this is 1, 2, 3, 4, the man running across here is, K1 plus K2 squared, whatever, downstairs, blah, 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 which is, plus I epsilon, whatever. But the way we're used to, and the way that's comfortable, and what we do in flat space-time, And that's great, because that's the target. What I'm building towards is so you can all join me in calculating, the UV finiteness of n equals 8 supergravity at 8 loops. I could use the help. So I'd like you to all climb on board that train. But my point is that this type of structure, right, is actually going to be fairly generic for all sorts of theories, even when you step away from Lorentz, even when you've got really horrible, nasty, disgusting two-point functions, which is how information propagates. You can still organize your information, one graphically, because graphs represent how information talks to information. And you can abstract away relations on top of that. So I'd like you to think of these flat space-time games as, non-trivial as they are, as not a solved problem. Quantum field theory of flat space-time is not a solved problem, but it's also a great place to start abstracting away ideas into methodologies that you can apply to all sorts of fun problems. Right? Well, not the. Well, we'll talk. Maybe I'll say some words towards the end about effective field theories of inflation and large-scale structure, both of which you can organize into double copies of stuff like this, of gauge theories, on top of non-trivial propagators. All right, but okay, so we learned Yang-Mills color factor. Every graph in Yang-Mills will come dressed with some color weight, some kinematic weight, some propagator structure. Propagator structure is trivial at 3 points. And what we're gonna do now is we're going to look at 4 points. We're just going to move forward to 4 points, and we're going to learn something critically important about the next and final property that these Fs have to satisfy in order to get gauge invariant predictions. And so now we'll go to the second part of this lecture, which is, let's go to 4 points and discover Jacobi. All right, before I go to 4 points, any questions on what we talked about at 3 points? Okay. By the way, I'm treating the way we're calculating at tree level exactly the same way that I treat calculations at loops, right? Which is again to try to come up with a way of dressing the answer that satisfies physical constraints. All right, so what needs to show up at 4 points? Okay, so, well, we're going to have 3 physical channels which we could factorize on. And generically in a theory, of course, we could have some contact contribution. I'm going to label these graphs with Mandelstam variables. And so, well, first, let me give external labels. Otherwise, they could have just been the same graph that I drew in weird ways. But now these are distinct graphs. They've got distinct labels. Good. And so this guy I'll call the S-channel graph, and this guy I'll call the U-channel graph. The T-channel graph, and this guy I'll call the U-channel graph. And S I will also use for the momentum running through the propagator. Right, so the propagator, the denominator of this graph will be an S, if S is K1 plus K2 squared. This guy will be K1 plus K4 squared. And this guy will be K1 plus K3 squared. Good. Now, the interesting thing about contacts is you have every right in your action to have higher field operators that sit there the first time they show up, not showing up over any propagator, right? right? And this is, in fact, exactly what shows up in Yang-Mills. In Yang-Mills, I have a 4-point contact term, right? From my, my 4 A's sitting there in my action after I expand out my F squared. But even though this shows up in the amplitude, I can take this information and assign it wherever I want from the sheer fact that S divided by S equals T divided by T equals U divided by U equals 1. So if I've got some contact information here, just generically for a theory, some contact information, I can assign some of it to the S channel graph divided by S, and some of it I can assign to the T channel graph, and some of it I assign to the U channel graph. And these assignations are, in general, not unique at all. There's all sorts of freedom how I can move this information around. Okay. I'm just pointing this out because, as you're probably familiar with, Yang-Mills, at the level of the action, has a propagator and has a 3-point interaction, has a 4-point interaction. Gravity has a 3-point interaction, a 4-point, and then a 5-point, and a 6-point, 7, and so on, infinite number, right, after I expand out my root minus GR. But if I express my amplitudes on the same scaffolding, which is cubic graphs, meaning I assign my contact in some way to cubic graphs, right? Again, I can do this because I just need to take whatever its contribution is and multiply it by the inverse propagator of the graph I'm assigning it to. Then I can talk about Yang-Mills amplitudes in terms of just cubic graphs. I can talk about gravity amplitudes in terms of just cubic graphs. And I have a chance, since I'm talking about them in terms of the same nouns, in terms of the same scaffolding, of starting to notice relationships between the theories. Relationships that are otherwise completely obscured if I'm just, looking at this. Yeah, question? What? How do I separate? So what you're going to insist is you're going to insist that however you separated it out, that when that it adds up to what I started with. Okay. It turns out, so I'm trying to avoid overly referring to the existence of Feynman rules in particular gauge, right? But for Yang-Mills, right, what does a 4-point contact contribution look like? It looks like CS times some game in terms of polarizations and some CT, some games in CU, games in terms of polarization, right? Right, just Lorentz gauge Feynman rules. Yeah, this is the contact term. Okay, this is not unique. Why isn't it unique? It's because these C's are related. So I can absolutely move stuff around. Right? It looks unique, but it's not unique at all. It's not telling me where things go. It's telling me one place things can go. Yeah? And what I'm going to show you is the relationship between these guys is forced on us by requiring gauge invariance. Okay, just from an amplitudes perspective. And the reason I'm going through this exercise is because, again, the muscles were, and this is something anybody can do. Anybody who's taken a quantum field theory, can play around with tree level 3-point and 4-point polarizations and the rules. It's a warm up for building the sorts of muscles that let you play with more challenging situations, like we'll encounter at higher loops, mostly next lecture. Okay? All right. Good. So let's zoom. So I was trying to avoid referring too much to particular Feynman rules and particular gauges, but what I will point out is the existence of Feynman rules suggests that there is a representation, or tells us there's a representation, where I can get from the kinematic contribution of this graph to the kinematic contribution of this graph via relabeling, right? So whatever, CS NS over C. How let me go over someplace I can write just a little higher to make this point clear. The existence of Feynman rules. I'll even label this point. The existence it implies the existence of automorphic representations of the graphs, by which I mean CT NT over T, right? So addressing my T-channel graph, some color weight, some kinematic weight over the denominator is absolutely going to be CT NSS under legs 1, 2, 3, 4, going to 4, going to 1, going to 2, and going to 3. And just to make that very obvious, here's how I wrote the S-channel graph over there. Here's how I wrote the T-channel graph, but I'm just rotating it to make it very obvious. Yes? Okay, so if there exist Feynman rules, right, the only difference between these two graphs are the labels, right? That's the only two. And so there have to be dressings that respect isomorphisms, right? Or in this case, it's the same graph, it's an automorphism. Okay, good. And so with that in mind, we're going to zoom in and think about what has to be invariably associated with this S-channel graph. All right, so even in theories, like gauge theories, like Yang-Mills theories, certainly gravity theories, effective field theories, even theories with contact terms, there exists obligatory data. I'm sorry, I realized I went right into the, oh, this is just words. As long as the equations are readable, you should be fine. Even theories with contact terms exist obligatory data associated, that have to be associated with particular graphs. Okay, so what do I mean? I mean the color weight associated with this graph and the obligatory, what absolutely has to be in this graph, that I can't move to a different graph under local, for local representations, has to be whatever in any representation, how I dress the graph, taking the S channel to 0. So on the physical pole where this channel becomes physical, where it goes on shell, that data has to be on this graph. I can't move it to any other graph in a local representation, right? Because it's physically there. Because no other graph contributes to this physical channel. Right? I've isolated it, right? And what is that data? That's just the sum of our states of our 3 trees. In fact, our color-dressed 3 trees. S bar. Okay. I'll make it very obvious that I'm doing is I'm taking one of my 3-point trees, I'm just labeling this leg L. Remember, it's momentum outgoing. So over here, what's outgoing is minus L. All right. This is a gauge invariant quantity. No choice of gauge changes what's in here. This is a gauge invariant quantity, no choice of gauge. There's no shuffling it around, it's just there. It's a physical part of the theory. If it's something different, it's a different theory. Yeah? Okay, and so I know I'm repeating myself, but there is obligatory data associated with the channel, and we can access it by looking at factorization, right? And this is what's at the heart of unitarity methods. Grabbing the stuff that has to be places, right? And then seeing, what's, well, we'll get there. We'll get there. But let's carry this out. So, just to remind you, this was dot epsilon 2 and then epsilon L dotted with K1 minus K2 plus cyclic times, right, and state. Now this guy, my polarization, my internal polarization as a state, and I'm summing over the states, right? And then let's say epsilon 3 dot epsilon 4, epsilon minus L as bar dot K 3 minus K4 plus cyclic. Right. So I'm just right, and then what was here was an F A1, A2, and then whatever AL, and F AL, A3, A4. Let me write this a little neater then. This again. So this is some CS. And the CS is F A1, A2, and then some eternal edge that I'm just summing over. F, E, A3, A4, right? Times, again, times the result of summing over these states. Yeah? But this is what the completeness relation told us to do, right? And so, in effect, it's sticking an eta mu nu every time I've got a pair of these guys, and just taking what it was dotted into and dotting what this guy was dotted into. Then subtracting out stuff to make sure that you're not introducing a gauge choice. That's all the P's and Q's. But the Q's aren't physical. Nothing physical depends. So all that Q dependence, whatever my Q's in, has to drop out under conservation of momentum. And in fact, it does. And so I'll just write down what you get after carrying out that state sum. But let me emphasize that this is true, that you're taking this and then you're imposing cut conditions. What are cut conditions? Those are the physical conditions on the momenta you get from actually getting to talk about this as a tree, and this is a tree. All right. So I'll tabulate the cut conditions after I write down the answer. So the answer, so I can write this in terms of epsilon 1 dot epsilon 2 A1 mu plus 2 epsilon 1 dot K2 epsilon 2 mu minus swapping 1 with 2, right? Because remember, it's antisymmetric. My S-channel diagram definitely has to be antisymmetric. Under 1 and 2, right, dotted in with epsilon 3 dot epsilon 4. Now this will be K3 mu plus 2 epsilon 3 dot K4 epsilon 4 mu. Great. Okay. So undercut conditions, this is the obligatory data that has to be associated with this graph. And so let me Let me write down what those cut conditions are. I mean, I think it's obvious, but it's always good. It's always good to see that we agree when we write down obvious things. All right, so what's going to be true? What's going to be true is K1 plus K2 plus K plus K4 equals 0. That's not coming from the cut. That's just coming from the fact that we're talking about something at 4 point. This is the fact that all of our external guys are massless and on shell. And I hope it's obvious that when I write something, I mean, I didn't even bother. Yes, these are, you know, whatever, D vectors. And this is a contraction, like a, you know, a Lorentz product between Ki and itself. So Ki, mu, Ki, obviously. Okay, good. But what do we have? We have K1 plus K2 plus L minus L K3 plus K4, right? We have S equals 0. We have T equals U. Minus U. Let me write that. Minus U. And we have L squared equals 0. Good. So these are the cut conditions. So what I have, how am I doing? 2 minutes? I'm gonna take like 7 minutes. Is that okay? All right. Good. So I can assign this indelibly to the cubic graph, to NS, but there's stuff that I could be missing. And it's worth noting that this thing that I assigned, yes, this is gauge invariant. This is gauge invariant at amplitude. This is gauge invariant at amplitude. This is gauge invariant only under on-shell conditions. In fact, if you take NS obligatory and you set epsilon 1 to K1, you get something, and it's this, right? You get something that's proportional to S. I won't bother writing it down. It's not hard for you to write it down. It's something that's proportional to S. So when S is 0, yeah, it's on shelves. It's a product of trees. But in general, it's not gauge invariant. I make this point because you can ask, well, I know my amplitude has to be gauge invariant. Maybe the easiest thing to do is to add a contact term such that each individual graph is gauge invariant, right? So the idea is I'm adding a contact. So I'm saying my actual NS is going to be my NS obligatory plus some N contact that I've assigned to the S graph times S. It's not a contact if I'm not multiplying by S to eat up the propagator, right? All right. And so the question is, can I add a contact to make N sub S gauge invariant? Right. Well, I mean, it's clear from the mass dimension we're playing with the only type of ansatz we can write down for our contact is going to be something like epsilon 1 dot epsilon 2. Call this alpha 2. Epsilon 1 to epsilon 2 then has to be epsilon 3, epsilon 4. Okay, what if epsilon 1 is kissing 3, then 2 is kissing 4, and if 1 is kissing 4, then we've got 2 kissing 3. And these are the only things we can write down, right? That's local, right? It's local and consistent with the mass dimension, what we're playing with. which is basically just 2 dots. Right, because it's coming in with this S. But there's no choice. There's no choice of alpha that satisfies the word ns such that epsilon I goes to ki. No alpha choice satisfies. And that's true. There is no local representation. There's no local representation that, that individual Feynman diagrams are gauge invariant for Yang-Mills. You can come up with non-local stuff if you want. You can start like throwing things in the denominator that cancels out once I add everything together. But there's no local representation. All right, what this means is that if our amplitude is to be gauge invariant, then our amplitude has to, our graphs have to speak to each other. What we need, so we can still demand that our full amplitude is 0, but that's going to mean cancellations between our graphs. Right, and that can only happen if our color weights speak to each other. So you can give an ansatz, say a linear ansatz to CT equals like beta 1 plus beta 2 CU. Right, so you let your color weights speak to each other, and you've given this contact appropriately relabeled, but with the same coefficients to each of your graphs, right? And this you can solve. And given the way I labeled things, where it's really, if you're really following the vertices, 4, 1, 2, 3, and 3, 1, 4, 2. So given the way I labeled things, can solve, and you discover that CS equals CT plus CU. Right, and so this is the Jacobi, given how I labeled my graphs, the colored Jacobi. Right, and you find out that the contact term is just going to be dot epsilon 3, 4 minus epsilon 1 dot epsilon 4, epsilon 2 dot epsilon 3. Okay, great. And then you've got something that's absolutely gauge invariant, and it's unique. It's absolutely unique. I mean, it inherits whatever coupling. So I didn't write it down. It inherits whatever coupling that it got from the 3-point. And when I say unique, I mean, of course, I can move stuff around between the S channel and T channel, right? Breaking the automorphic symmetry, it's not required to have automorphic symmetry. The fact that there are Feynman rules just means there is a representation that has automorphic symmetry. But something that's very special, besides the fact that we discovered that the way the Fs have to play with each other is to satisfy a Lie algebra's Jacobi identity. Right? So that's actually part and parcel about being a vector, is we see that our numerator factors satisfy the very same Jacobi identity. Right? And in fact, there's no way of assigning the contact information. So you could start from this and start moving things around. There's no way of assigning it at a 4-point. There's no gauge, if you like, where once you push things to cubic graphs, that 4 points for Yang-Mills, your kinematic numerator weights satisfy Jacobian antisymmetry, just like your color weights. And so that's actually what we mean, or it's one example of a duality between color and kinematics. All right, I'm going to wrap it up with just what I'm putting right here. Gauge invariance from color speaking color according to some algebra. All right. If you have kinematic weights that obey the same algebraic properties as their color weights, then you can take, for example, Yang-Mills, replace the color weights with other kinematic weights that are spin 1, right? They've got polarizations, they're spin 1. And you'll get amplitudes in a gravitational theory. And you'll be lifting linearized gauge invariance to linearized diffeomorphism. I'm going to say a little bit more about this next time, probably a lot more. But let me say, so what we talked about today was purely in the adjoint because gluons are in the adjoint. Gluons have FABCs. And we discovered the two primary, independent of whether it's SU2 or SU bazillion, the FABCs have to satisfy antisymmetry and they have to satisfy Jacobi. Turns out to all multiplicity Yang-Mills, you can always find representations of your kinematic weights. You can always find a way to assign the contact information that graph by graph, they satisfy exactly the same Jacobi relations as the color weights. Which means that you can always perform this double copy procedure at tree level. It's intimately related to field theory KLT, which is the alpha prime goes to zero limit of string theory KLT, which is, again, tied directly in to this type of adjoint representation. But this idea of focusing on gauge invariance and the types of color structures, how they allow gauge invariance to manifest, and then finding things dual in color to that goes far beyond adjoint, right? So you can do DABC, color dual. You can do stuff in the fundamental. BLG theories, right, have, they satisfy a 3 algebra, not a Lie algebra, right? So, but you can find color dual representations of the kinematics in this theory. So there's a 3-dimensional theory. Find color dual representations, you double copy this theory, and you land on exactly the same supergravity theories you land on by double copying 3-dimensional super Yang-Mills the normal way in terms of this adjoint double copy. Which means that this BLG striation, the kinematic building blocks color dual to the BLG 3 algebra, is one way of prying apart. Ultimately the permutation invariance associated with gravity theories. But and Yang-Mills dual to Lie algebras, there's the FABCs, is another. Good. So what we have to look forward to tomorrow is actually taking this show on the road. We're going to start looking at higher multiplicity amplitudes, how to turn those into loop amplitudes, and how we can use these field theory relations to recycle information efficiently.
Okay, thanks a lot. Any questions for JJ before going for lunch?
Okay, I've got a question for myself.
Shruti has a question.
Oh, okay.
Shruti and then JJ.
All right, thank you.
So somewhat speculative, but
Yes.
Is this the only way? So here you've replaced CS by NS.
Mm-hmm.
Is that the only way you can lift gauge invariance to linear diffeomorphisms, or could you replace like CS by NT? and
Oh.
etc.? Is there some like twisted way you could do it?
Well, you can certainly replace CS with NT plus NU. Yeah? No, but again, it doesn't have to be Yang-Mills. I mean, and this is something I know you know, but this is something I didn't emphasize at all, is that there are all sorts of theories you can find color dual representations of. So covariantized free scalar, nonlinear sigma model pions. You can find kinematic weights that are dual to this adjoint type striation. And then you can start taking products. So Yang-Mills with Yang-Mills gives you gravity, but nonlinear sigma model pions with Yang-Mills gives you Born-Infeld, or super Yang-Mills gives you Born-Infeld, Volkov-Akulov, Dirac scalars. String theory, the open string, you can think of as a field theory double copy. So the open string, the field theory double copy, where you've got one color, one weight. It's a color weight that carries all sorts of higher derivative corrections. This is a color weight that satisfies Jacobian antisymmetry because it's a function of colors. Actually, because it's a function of DABC colors, too. So it's not just adjoint stuff. And because it's a function of kinematics and alpha prime, right? But it's something that satisfies antisymmetry in Jacobi. This is just Yang-Mills or super Yang-Mills, right? And then just over your massless propagator. Right, so you can pull apart all sorts of theories into these building blocks. The nice thing about this is you can look at this as an effective field theory. It's just higher orders of corrections. All your alpha prime headaches live here, and all your polarization headaches live in something you've already learned how to appreciate their polarization headaches. But yeah, so there's a lot more freedom. There's a lot more freedom when the gauge invariance doesn't require a very rigid structure, right? Like so the more symmetry, the more symmetric structure constants are, the easier it is to just flop things together. But yeah, I don't know if I answered your question.
Okay, more questions? Yeah.
With all these examples that you just mentioned, is there some organizing principle that tells you, given this theory, I know what the single copies are, or given the constraint theories, what a double?
It depends. It depends on what you mean by knowing what a theory is, right? And in general, it's a lot easier. It's a lot easier to take the product of things and see what comes out and say, oh, wait, does this have symmetries I recognize? Does that, oh, wait, this matches amplitudes I know from this theory. And then you can prove that, you can line it up and prove that you've double copied to the theory you think. Modding out by building blocks is a little trickier, right? Because it's a lot trickier. It's harder, right? But you can definitely do it. But generically, well, maybe this is an offline discussion. There are ways of modding things out. The way of modding things out and guaranteeing you have something that's local at the end involves ons, let's say, generically, right? But yeah, there's what I will tell you about next time is a test to see, given ordered amplitudes, and I have talked nothing at all about what ordered amplitudes, but given ordered amplitudes in a theory, can I come up with color dual adjoint representations for that theory? And if they satisfy certain relations, you absolutely can, and it's absolutely prescriptive, and it actually goes both ways. And the way I'll talk about is the fact that these satisfy Jacobi means something very special about how the ordered amplitudes have to play with each other. But it goes both ways. I can take ordered amplitudes and jam them into something that satisfies Jacobian antisymmetry if they have the right properties. Beyond adjoint and tree level, there's all sorts of stuff that's still being worked out.
So there is one more last question on the Zoom. Can a similar duality be realized for weak charge?
Oh, yes.
Okay.
No. So again, it depends on what you mean. Do you mean can you find like pre-spontaneous symmetry breaking? Absolutely trivially so, right? Because it's just massless stuff with some gauge group, right? After spontaneous symmetry breaking, I think the question, and I'm not sure who asked the question, but yeah, I mean, feel free to send me a message. But you can play all sorts of games on top of massive propagators for massive stuff that's color dual.
Yeah, if you want to unmute yourself and ask more specific, you can do it now, or maybe tomorrow. And JJ will also start with his question tomorrow. Okay, thank you very much, JJ, and we will now stop for lunch and reconvene tomorrow morning.